Hi there! Welcome to the fourth episode of the Digital Electronics Fundamentals series. If you remember me talking about making any kind of logic gate with just the NAND or NOR gates, you remember right. If you want to know how, sit comfortable and start watching this video, beginning to the end. Let's begin.
Hi there! I am Carlo Carrano and this is Electronics Engineering Made Easy.
Let's start by using the NAND gate. Here is the schematic representation. And here is its truth table. Let's now take a look at the first and the last row. If we give the same value to both inputs, we obtain an output that is just the opposite of the inputs. And this is basically the definition of an inverter or the NOT gate. And so we can build a NOT gate just using an AND device that has the two inputs connected together. If we build the truth table of such a circuit, we see that when A is at 0, according to the first row of the NAND gate truth table, the output will be a 1. And similarly, if we put a 1 on the A input, the output will be of course a 0. And this table is exactly the one of the NOT gate. Now that we know this, we can easily build an AND gate using all the NAND gates. Let's start by drawing the AND gate and its truth table. If we compare this truth table with the one of the NAND gate, we see that the output values are of course the opposite. And therefore we can obtain an AND gate using a NAND gate and negating its output. Well, we knew that already, right? We can therefore obtain an AND gate just by using a couple of NAND gates. The first one will actually work as an AND, and the second will be used as a NOT to invert the output of the first gate. As simple as that. So you see how so far we were able to use the NAND gate to make the NOT gate and the AND gate. And we can actually do much more than that. However, before getting into it, I need to tell you something about the DeMorgan Theorem. The DeMorgan Theorem is at the base of the majority of the combinational circuits. It is a way to transform them in a way that is more appropriate for making them or for using them, although maintaining their properties. The theorem has two forms. In the first form, we start from a NOR gate, represented in Boolean algebra like this, and we say that we can transform this expression in another one that has the same truth table but is built differently. The empirical rule is to change the OR into an AND, and then we split the NOT bar between the two values A and B like this. The second form of the theorem starts from the NAND Boolean expression. This time we change the AND into an OR, and we split the NOT bar between the inputs A and B like this. Now let's try to demonstrate the theorem in a very easy way to understand. And to do that, we begin with the first part, the first expression. The left side of this expression represents a NOR gate, so let's write down its truth table. And now let's take a look at the right side of the equation, and let's build the truth table for it. If both A and B are 0, and since they are both inverted, they both become a 1. Then 1 and 1 is a 1, and so we can write the output for the first row. On the second row we have a 0 and a 1. Both need to be inverted, and so they become respectively a 1 and a 0. And the AND operation of 1 and 0 is a 0, and so we write a 0 for the output of the second row. The third row behaves exactly the same, and so the output is still a 0. Finally, in the fourth row we have two 1s. By inverting them, we obtain two zeros, of course, and the AND operation of two zeros is still a 0, which we can write on the last row of the truth table. Now, you see how the two truth tables are identical? This means that the formula number 1 of the DeMorgan theorem is correct. Let's do now the same with the second formula. We start this time with the truth table of a NAND gate. And now we build the truth table for the right side of the expression, working the same way we did with the first expression. And so, in the first row, where the inputs are 0 and 0, we have an output of 1. In the second row, with the inputs 0 and 1, we have an output of 1. In the third row, with inputs 1 and 0, we also have an output of 1. And the last row, which has both 1s as inputs, has instead an output of 0. Comparing the truth table, we see that, again, are identical, and so we have proved that the second part of the DeMorgan theorem is also correct. We can use yet another way to test the correctness of the two equations by translating them in their circuital equivalent and either build the circuit and test it, or use a simulator for digital circuits. Let's do it now with the simulator. Here is the circuit we will be using for the simulation. It is made of two parts. The one above is related to the left side of the first equation. The part below is related to the right side of the first equation. And so, since the left of the equation is basically a NOR gate, I have used just a NOR symbol connected to two inputs A and B and to an output. The bottom part is basically the logic AND of not A and not B. And so I have drawn an AND gate where the two inputs are inverse of the same inputs used for the upper section of the circuit. So what we need to do now is to assign all the combination of inputs A and B to both circuits simultaneously and see if for each of the combinations the output of the upper and lower part of the circuit are the same. And you see that with A and B both as 0, we have both outputs set at 1. Changing B to 1 makes both outputs go to 0. And similarly, keeping B to 0 and changing A to 1, both outputs are still going to 0. Finally, if both inputs are set to 1, the outputs are both 0. And this shows that the upper and lower circuits behave exactly the same, which proves that the two sides of the first DeMorgan expression are really equivalent. A similar simulation can be done for the second part of the theorem. Here is a circuit that can be used to do it, but I leave the actual procedure as an exercise for you to try it. Let's see now how we can make an OR gate using a circuit with only NAND gates. Here is the symbol of the OR gate, and here is its truth table. Now let's write the Boolean expression for this truth table and let's apply to it the DeMorgan theorem. To do that, we need to have a NOR. For that, we can just add a couple of notes to the expression, like this. And now we can consider the first note as part of the NOR gate, and the second note to negate the output of the NOR gate to make it again an OR gate. At this point, we can apply the DeMorgan theorem to the NOR part of this expression, writing therefore not A and not B, and then we add the remaining note from the previous expression like this. This is the expression for the OR gate in terms of NAND gates, and in fact we can translate this Boolean expression in a schematic taking the two inputs A and B, inverting them with a NOT, for which we can use an AND gate with the two inputs connected together, and then the two outputs will be inputs of another NAND gate, like this. Let's see now if this circuit behaves like an OR gate for real. And to do that, let's build its truth table. Now let's apply the two inputs of row 1 to the circuit. They will both be a 0. On the other side of these gates we will have two 1s, because the two NANDs behave like NOT gates. And now we have another NAND gate with both of its inputs set to 1. And so 1 and 1 is 1, inverted becomes a 0, and so the final output is a 0. Let's now go to the second row, and so we input a 0 and a 1 into the circuit. The 0 becomes a 1, and the 1 becomes a 0 because of the two NOTs. And so we have the final gate with inputs of 0 and 1, which provide an output of 1. And of course, if we switch the two inputs now to find the result of the third row, because the circuit is symmetric, we will again obtain an output of 1. Yeah, I just realized I forgot to write down on the circuit the previous output. Here, fixed. Now, let's see what happens with the last row, for which we need to input two 1s into the circuit. The two 1s becomes both a 0, and the two zeros are applied to the final NAND gate, which of course will output a 1. Now, comparing the two truth tables, we see that they are identical, and so the new circuit with row represents an OR gate, and it is made all of NAND gates. And here is how we can use the simulator to double check that the circuit behaves exactly like an OR gate. Note how I change the values of the inputs and how the outputs change accordingly and are consistent with each other. To make an NOR gate using only NAND gates is very simple, now that we already know how the circuit is made to make the OR gates. Here is the NOR symbol and its truth table. And as we already know, we can just invert the OR output to make the NOR. So, we just use the previous schematic, and we just add one more NAND gate to act as a NOT for the final output. Another way to see this is to write down the Boolean expression of the NOR gate and apply the DeMorgan Theorem to it. And we see that the NOR becomes an AND, which operates on the inverted inputs of the original NOR. And so basically this part here is just the AND gate that we see through the DeMorgan Theorem. And here is the simulator again, this time with the NOR gate and the circuit made with NANDs that represents the NOR gate itself. And once again we can see how the two outputs match exactly when we change the value of the two inputs. Let's now work on the XOR gate to see how to render it with NAND gates. This is the symbol of the XOR gate, and this is the truth table where we can see that the output is a 1 only if one input or the other is at 1, but not both at the same time. To see how to build this gate with NANDs, we start one more time with the truth table. These are the rows with an output of 1, and this is the Boolean expression derived from the truth table. We can manipulate this expression using the DeMorgan Theorem, and in particular we will need to convert the OR symbol, the plus, into an AND operation, which can be executed with NAND gates. We can put two NOT symbols on top of the whole expression, which does not change the results, and then we can associate one of these NOTs with the OR symbol, making it a NOR. Then we can apply the DeMorgan Theorem like this. And now the expression is all in terms of AND and NANDs, which we can represent solely with NAND gates. Because we use each input as is and also inverted, we have to have available both for each input, and so we draw the first part of the schematic like this: A and not A, and then the B and the not B. Now we need to draw the part related to the NAND operation between not A and B. So we draw the gate, and then we use the appropriate inputs for it, not A and B. Similarly, we need to draw the equivalent of the NAND between A and not B. At this point, we will need to do the NAND of these two elements, the NAND output we just finished drawing. And for that, we put one more NAND over here, and we connect it to the two outputs of those two other NANDs. The output of this last NAND is the actual output for the circuit, which is supposed to be equivalent to an XOR. To verify that this circuit is really equivalent to an XOR gate, let's build its truth table. So we have two inputs A and B and one output U. On the first row we have both inputs set to 0, which brings us 0 here and here. When the zeros go through the first two NANDs, they become 1s, and so we have a 1 in these 2 points, here and here of the circuit. On this NAND we now have a 0 and a 1, and so the output is a 1. Same thing for this other NAND gate. And so now, at the last gate, we have both inputs set to 1, which makes the output a 0. And now we repeat the same procedure with the inputs of the second row of the truth table. So here we have a 0 and here a 1. Here we have a 1, another 1, a 0, and a 1. At this NAND output we therefore have a 0, and at this other one we have a 1. And finally, the last gate has a 0 and a 1 as inputs, and so the output must be a 1. The third row has also a 0, 1 as an input, and so because of the symmetry the output will also be a 1. Let's examine now the last row, where we have a 1 on both inputs. So this is a 1, and this is a 1 too. We have a 0 here, and a 0 here. And so this NAND on the top has an output of 1, and the one on the bottom has an output of 1. The final NAND, since both inputs are 1, has an output of 0. And now you can see how the truth table of the XOR gate and the one of this circuit match exactly, and so the circuit with only NANDs works exactly as an XOR gate. And of course, the verification could be done also using the simulator. Here is the simulator bench with a schematic on it with both the single XOR gate and the whole equivalent circuit. And you can see that whatever I set the two inputs, once again translates in the same output for both the XOR and the equivalent circuit, confirming that they work exactly the same. Let's now work on one more gate, the XNOR. Since I don't want to bother you with the same exact procedure, I'm just fast-forwarding all the steps, so if you so desire, you can follow by running this part on the video, frame by frame. Just note that for this gate, rather than adding a NOT at the output of the previous circuit, we just need to reroute the wires of the previous circuit so to obtain the new one with the same amount of NAND gates. I'll totally leave the simulation up to you if you wanna run it. By now you should know how to do it, and the link of the simulator is in the description below so you can use it. One last thing that is left to do is to show you how to make any of the gates we studied using only NOR gates. The procedure is similar to the one we used for the equivalence with the NAND gate circuits, but this time we will need to manipulate the Boolean expressions so that they will be all represented with OR and NOR gates, and so when necessary we will use the other expression for the DeMorgan Theorem, the one that converts NANDs into OR and NOTs. Because of this peculiarity of the NAND and NOR gates that they can reproduce any other gate type, NAND and NOR gates are called universal gates. Sometimes, when designing a digital combinational circuit, we sometimes have available a certain amount of one of these two gates, and if we need to instead use a different kind of gate, we can use these equivalent circuits. This way, we can in theory build a whole digital circuit using only NAND gates or only NOR gates. But there is more. Remember the two main types of digital integrated circuits? The TTL circuits and the CMOS circuits? Well, because of the peculiarity of the TTL circuits, the easiest gate that can be created on a chip is the NAND gate. Because of that, sometimes the designers of these chips prefer to make available all the other kind of gates using internally the equivalent NAND circuits we saw in this video. Similarly, because of the peculiarity of the CMOS gates, the easiest gate to produce in CMOS is the NOR gate. And guess what? They tend to make all the other gates using circuits with NOR gates. It is simpler and costs less. Now that you know all these new facts, next time we can start working on more complex circuits, made as a combination of several ports of the kind we have seen so far. And now that you know everything on these basic ports, it will be much easier to understand the more complicated circuits. So, get ready for something new and exciting in the next episode for the series, and happy experiments. Oh, I almost forgot. If you don't want to miss the next episode, don't forget to subscribe and to click on the notification bell. Remember, you will also have to activate the YouTube notification on your smartphone, or the notifications will not reach you. And now, see you in the next episodes.